Hey, hi, welcome to the part 2 of day 5 of the DP workshop where we are learning to code DP iteratively today. And in this particular video, we're going to take another problem and try to solve the problem first of all, and then convert it to an iterative coding so that we can solve it then and there. Okay. So in this particular problem, what we are given is there are n types of coins denomination, let's say x1, x2 up till xn. Can you make a sum of m with these coin denominations is what we need to determine. And this is a very standard problem, to be very precise. When I say coin denomination, it's more like, let's say you have a 1 rupee coin and a 2 rupee coin and a 5 rupee coin, and can you make something like, let's say 7, and it turns out we can write 7 as 1 plus 2 plus 2 plus 2, right? So we can also write it as 5 plus 2. So it is possible to create 7 with these these coins. Let's say if I would have put 3 over here, so still it's possible. But what if I put 4 over here? Yeah, it's still possible. We can write 3 plus 4, right? But what if I put 4 over here? Or let's say something like 6 over here. It's no longer possible to make a 7, right? So you're given bunch of coins, values that are feasible. Can you make a particular sum m with them, right? And over here, how is it different from the problems that we have been seeing till now? In most cases, you might have seen the problem called as knapsack as of now, which is for every item you can take or not take it. In this case, every coin denomination can be taken multiple number of times, right? That's one change that happens in this problem. So how do we attempt this particular problem? First of all, we have to recognize which form this problem lies in. So what form this lies in, okay? What form? So it's a very similar thing. Like we have to kind of give it a index and try to decide what how many times do we take the ith item or things like that. So we're gonna keep it in form 1. Okay, we're gonna keep it in form 1 itself because the way we do it. Next is we're gonna quickly talk about the states, right? What is the states? So we have solved similar problem before in the workshop, and the way we do that is dp of we keep the level and we keep how much of sum to make, sum left to make, right? And can we make in the level from the denomination level till, let's say, n minus 1, or n in this case since it's one indexed, okay? I can write n over here. With these denominations, can you make sum left, right? Can you make this much? Yes or no? That is what this is going to return. Can you make a sum m? Can you make a sum left as a parameter from this level till n? This is how you formulate DP states, right? In this case, this is what we're going to keep over here. For transitions, let's try to understand this one. This becomes a little interesting if you have not seen this version before, which is 0 infinity or infinite supply of every item. So in this case, what we can do is we can try and take, let's say you are at a certain item, okay? This is the level that you are at, okay? And you are left with this much of sum left, okay? Now for this item, I can take it once, I can take it twice, I can take it thrice, and so on up till number of times, so that the sum left is no longer to take it. So one way to write the transition for for this problem specifically is this, that dp of, let's say, some level L, I'm just writing L over here instead of level so that to keep it short, and S as sum left, okay? And let's say this is some value X over here, okay? So some value X over here, this is nothing but the X of lth level X, okay? So in this case, I can try taking X once, and I will go to dp, maybe taking it 0 times, I will go to level plus 1, and I will still have to make the same sum left because I did not take anything from over here. If I take it once, in that case, I'm gonna go ahead to L plus 1 with with S minus, okay? S minus X. I have taken once, so I have to make the rest out of it. If I take it twice, I am gonna go to dp of L plus 1 comma S minus 2X. If I take it thrice, I'm gonna model it in a way that L plus 1, we go to L plus 1 and I take S minus 3X, and up this we keep doing this until, let's say, some S by X number of times, so that dp of L plus 1 S minus S by X, whatever this value comes out to be, X. This is the last remainder. After this, everything, if you take more than that, then the sum would become negative. The sum left to create is negative, and that is an infeasible case. So pruning will handle that maybe, or things like that might happen. So those will give you 0. It's not possible. So we'll check all of these things, and out of that, whatever is feasible, so take it once, twice, thrice. We're iterating over the number of times we take it. Okay, but this is a very a difficult way to do this particular problem. Let's try to analyze the time complexity with this transitions. Let's try to see that first. So if you write the transitions this way, let's try to see. Over here we have L, which can take n different values, and the sum left, which is given as m in the problem over here, right? We are given m over here, which is the sum that we need to check. So this is m over here, okay? And there are like certain number of transitions over here. How many transitions are there? S by x. So let's say the common denomination in the worst case could be 1, okay? And s in the worst case could be m as well. So the number of transitions over here is nothing but m, right? So the number of states is actually equal to order n into m, right? And the number of transitions in this case on an average, on, you can say worst case itself, but on an average it would be somewhat like, let's say m, okay? On the worst case can be m. The total time complexity will be order n into m square, something like this, okay? It would be order n into m square. But there is a very neat way to optimize this even further. There is a very neat way to optimize this even further to make sure that we get a better time complexity. How is that? Let's look into it, okay? The another way to see this particular process would be that you are at this particular place, okay? And you are left with sum left, okay? And there is an x item over here. Again, the same transition could be there. dp of, let's say, L comma S is there, sum left. You don't take it, you take it 0 times. So in that case, I'm gonna not take it anymore. So I'm gonna go to dp of L plus 1 and I'm not going to change S. If I take it once, I can take it even more times, right? So why not keep my L at the same place? Why not keep my L at the same place and just decrease my S? Okay, I took it once, so I decreased my S minus X, the sum left, but I'm at the same level still. I'm waiting at the same level because I can take it even one more time. And the time it, like, let's say I can take it now, I can take it 0 number of times, or I can take one more number of times. In that case, I will reach dp of L comma S minus 2x. And if you don't take any number of times, you're gonna go to dp of L plus 1 comma S minus X. From over here, I can decide again to take one more or not take. If you don't take, then you're gonna go to dp of L plus 1 comma S minus 2x. And if you take over here, then you're gonna go to dp of L comma S minus 2x, 3x, sorry. Right? Now if you see the different, like, if you don't take, then this is what you reach. If you take and then don't take, then you reach this. If you take and then don't take, then you reach this, and so on. So these are all the different states that we were earlier able to visit, right? So if you take the best possibly out of these two, I mean, if you can create it either with these two, either, okay? I mean, essentially or over here, either or we are going to do it over here. If you can solve it with either of these two, then you are good to go. And now you make the number of transitions only 2, right? We don't need to loop over all of these things. This thing over here, keeping the level at the same thing once, if you take it once, so that you allow it to take it again if it's feasible, if it's like optimal, is a very nice trick for elements having infinite supply. So this is what we can do for such items, that when you have a certain item with infinite supply, let the level be there, and then finally you can decide at any point in time that, okay, I'm not going to take it anymore, and move to the next level. So that's what this transition looks like, and this is how you can compute it. And now the number of transitions would be numbered only 2. Okay, so this is the only 2 transitions that you're gonna have, and that would be the total transitions, in fact, nothing more. If you do now do the time complexity check, that would be very simple. Number of states is actually still same, but number of transitions is now 2. So the total complexity will be n into m. Okay, that's the total time complexity now. So that's the thing. Next thing that we're gonna need to do before we move forward is the order of iteration. Over here we have the transition. We have the transitions. So we see the transition to determine the order of computation. Okay. So let's draw a L comma S. Okay, L comma S. So this is the level L. This is the S. Okay. It depends upon L plus 1 comma S, this one, and L, this one, L plus 1 comma S, and same L, S minus X. Okay. So this cell depends upon this value and this value. Okay. So let's say there is a full matrix over here. This cell depends upon this cell and this cell. So how do you iterate over the matrix so that you can find out the answer for every cell? The way we can do that is we can go in this way. Okay, so we can decrease the, so if you compute the value for L plus 1 first and then you compute the value of L, then when you're computing this, these would be available. So we go this way for L, for the rows, and for the columns we go this way. So we will do L going from 0 till, so from n till 0, and for the sum we're gonna go from 0 till whatever m given to us in the problem. This is how we can iterate for this particular formulation. It depends. This particular problem can equally be done in a by looping through 0 to n. The meaning and things will change a bit, but you can actually do it with this particular way as well. I'm not saying that this is the only way to do it, but the way we have learned it for now, this is how you can convert it to any particular iterative code. Okay, n to 0. So now if I have to write this particular code, let's go back now. Once we have this order, we can now go ahead and code this particular thing. So this is the place where we stopped at the last problem. Let's quickly go ahead and like remove the things over here. Okay. Okay, so we have this void solve. Now in this case, I am given an nm, and I need to solve the answer for let's say this integer x array is given to me. Okay. So now what the way we do this is we have to go through this loops. Okay. So we create an DP array, DP of n comma m. This is what we create over here. Now the beauty with iterative code is that it helps us allow us to write things all together in the function itself. So we can write DP of n comma m. Note that you have to make sure that you include the spaces that are there for like base cases. Okay. Very, very important. In the previous codes that we were writing, base cases were handled by the recursion and they did not get saved in the DP array. But for this particular problem, you will have to ensure that the base cases also have the memory allocation, memory in the like matrix or whatever you're keeping. So the base case in this case, in such problems, is level equal to n, and the m can at most be m as well. So in that case, these are the maximum things that we can go till. Now the loop of the thing would be integer level equal to n, we wrote over here, right? N, it goes from n to 0 and 0 to m. So L is going to go from n, L is greater than equal to 0, L minus minus. Okay. For integer, S is going to be equal to 0, S is less than equal to m, S plus plus. Now we have to compute for the base, for the case we are in the state L comma S, find out the answer for this. Okay. So how do we find out? First of all, check if it's base case. How do we check base case? If L is equal to n, that's the base case, right? The usual way we write it. When L is equal to n, how do we find out the answer? We cannot take any more items. So the sum left has to be equal to 0. So if S is equal to 0, in that case, dp of L comma S is equal to 1, or else dp of L comma S is equal to 0. Because if you don't have anything else left to be taken, then you can only make 0, right? You cannot make anything else. So you can make L comma 0, else rest everything is not possible. Then what we do is, if it is not the base case, then we have to compute it for a general thing. So now we go for general stuff. In this case, for a particular L comma S, we can either take this item. Okay. In that case, if the sum left is greater than equal to the x of the lth level, or we can like the item at that particular level. Okay. If the sum left is greater than equal to the item at over there, then we can take it once. Okay. So first of all, if you don't take anything, so dp of L comma S is equal to, by default, it's not possible. If dp of L L plus 1 comma S, like if you skip this item and you go to this particular state, and if it's feasible to solve it from there, then dp of L comma S is equal to 1. Ideally we can do it with an answer and then we assign it to like dp of this. That's what we do, but we can also use a dp array directly like a variable. Okay, if this is possible, if this is there, and dp of L plus L, we stay at L but we take this once. Okay, and if it's still possible, then we get answer is equal to 1 as well. Okay, and then we make dp of L comma S equal to answer. And by the way, as I said, we can use this dp array over here itself just to make the code more simpler. If you actually see the like iterative codes, they don't really write answer variables. It's more for recursive codes personally, I feel. But yeah, this is how we can compute the answer. So dp of L comma S is going to be by default 0. It's not feasible, but if you can make it by skipping this item, or if you can take it this item and then still make it, we are good to go. Note the L over here, so it depends upon the same row. So if the same row but a smaller s, it will already be computed in this particular loop. For a next row, some certain value, since we are decreasing the rows, it will already be available. So all these two values are available, so we can use iterative code like this. And at the end, we will be getting the final dp array. You can simply see out dp of 0. So 0, and you have the sum left. The sum that you have to make is m. So that's the standard recursion call that you would have made, but you just now access the dp array instead of that. Okay, so that's the full code for this particular problem. Like if you have n items m and you have to make m and you have n denominations, this is how you do it. Okay, so now we did not really write the recursive formulation, right? We did the same thing. We would have written this as the base case, this as the compute, and then saved it in a dp array, cache check and stuff, all those things we would have done. But if you now know how to write iterative code, it just makes it much more simpler. The one step that you add over here is to think about what order of loops do you use, because whenever you're computing something, the things that are required should already be computed. So that determines the loop of order of loop. Okay, and over here we just use the same logic that we would have decided from the transitions that we generally do. So converting, as you can see, converting like recursive codes to iterative codes is not that difficult. It's just a matter of understanding this ordering, number one, and just to know how to solve these things. And this is, by the way, the standard form, right? Form 1 that we have learned, very, very common, and you would be seeing many more problems using the same form itself, right? So that's almost all that is there for this particular problem. If you have any particular doubt, feel free to let me know in the comments. We will take that up in the doubt sessions that we usually do. This particular problem is a very standard problem. I would encourage you to try and solve the recursive version as well if you want. But one thing that I want to quickly talk about is why are we kind of going into iterative codes? Number one, they are quite fast in case every state is visited. So there are times where you will get runtime error or like seek-sieve errors or segmentation fault sometimes if the recursion stack is very, very high, because if all the states n into m states are visited in the same recursion, then you can get a recursion limit. The stack size will exceed, so stack limit exceeded kind of an error would be there. Okay, stack memory limit exceeded would be an error for you, and you would get a runtime error in that case. So to save you from all those problems, these iterative codes are there. So so the main idea over here is prefer iterative codes for the problems where all states are definitely visited. But for certain problems, when you call a recursion, only certain states are visited that are reachable. Okay, in those problems, you can use just recursive codes. Okay. Also, at times, I feel sometimes recursive codes are easier to write. Sometimes iterative codes becomes easier to write. So you should know how to write iterative and recursive codes both interchangeably and then use it according to your wish. Okay. I have personally seen that there are sites like CACS where you have to write iterative code or else you will not get AC. Reason being that recursion call also adds to time limit. So if you have something which requires a complexity of 10 to the power 8, okay, then you will have to write codes iteratively. You cannot write a recursion which goes into 10 to the power 8 depth. It will not pass. Okay. So write iterative codes and that should be enough for computing it in like at the boundary cases. For general problems, you can write both of them. That should be enough to solve any particular problem. Okay. So that's all for this particular video. I think we're gonna like stop at this particular place, but we're gonna solve another problem in the next video, which is going to be very, very interesting. I think one of the like most interesting problem that I personally loved when I learned it. So definitely check out that particular video, and also leave a like button, if like, hit the like button if you have not liked this particular video, because these problems and these videos do take a lot of time to create, and that just encourages me to make more such. Okay, that's all from my side. Thank you and see you in the next one. Bye bye.